what I call the neuro function or the brainstem function in the respiratory centers. The respiratory center is located on the medulla. You guys heard of Waterboy, right? Medulla oblongata, right? Yeah. If you haven't, look that up on YouTube where to do that. So you have, on the medulla, you have the respiratory center called the pons, P-O-N-S, okay? And on that pons is the apneustic center, which controls inhalation, and the pneumotaxic center, which sort of controls exhalation, okay? Like I said before break, I had to look it up. Chemoreceptors, you have two primary chemoreceptors in the body. One is the carotid body, and this is the carotid artery, runs up the neck, right? Then it bifurcates, and at this bifurcation sits these specialized cells called chemoreceptors. They're sensitive to different changes in gases, chemicals, right? And then you have one in the aortic arch in the body. So these are measuring. They're constantly measuring. Now they do measure partial pressure of oxygen. That's what PaO2 means, partial pressure of oxygen. That's for another day, okay? But when indirectly it measures levels of CO2. Because we breathe off the response to CO2, the hypercarbonic drive. So when it's time, what will happen is the apneustic center will cause the inhalation process, the active process, where you have the contraction of the diaphragm and the intercostal muscles, okay? And then it will do that up to the point where the stretch receptors say, well, that's enough. And then the pneumotaxic center will take over and send signals for the diaphragm to relax and the muscles of the thorax to relax, okay? And so we need this response as well, and that's, we'll get into this a lot deeper. I just want you to have sort of the concept for right now that we have a mechanical system dealing with the size of the container or the thorax, and then we have a neurological part dealing with the respiratory centers on the brainstem, and then working together through the chemoreceptors, we inhale and exhale. So it's quite complicated. Once we, I don't know, last time or last week or something, that the majority of the carbon dioxide is actually carried back to the lungs and the plasma. It's called the Chloride Shift, and there's a little video of it. Now, just take it in. But I believe she talks a little fast. Get what you can.
I've gotten a lot of questions about the chloride shift. Why is it necessary? What happens if it doesn't happen? And so we are going to, well, I'm going to just draw a. So here's some tissue. And here's a capillary that's running right next to that tissue. Inside this pressure of CO2 in this capillary is about 40 millimeters of mercury. The partial pressure of CO2 in the tissue or in the interstitial fluid is about 45 millimeters of mercury. So since we have this difference in the partial pressures of CO2, it's higher in the interstitial fluid than it is the capillary, CO2 will diffuse from the tissue into the capillary. Now we have three different ways. A little bit of that CO2 gets transported as just plain dissolved CO2. dissolved CO2. And about 23% of it so that just binds to the peptide part, to the alpha and beta chains. 70% of it is what we care about right now. And that's the part that gets carried around as bicarbonate, or HCO3. The majority of our hemoglobin, we first need to carbonic acid. And the enzyme that catalyzes this reaction is called carbonic anhydrase. Is this reaction right here is happening inside of a red blood cell, okay? The enzyme carbonic anhydrase is inside that red blood cell. And so it doesn't just, the CO2 in order to be converted into carbonic acid. That carbonic acid then will immediately break down into the bicarbonate ion. This equation as CO2 plus water is in equilibrium with bicarbonate and a proton. That's why the intracellular pH of a red blood cell doesn't drop way down as you make this exits, so let's draw a big red blood cell around this, and we're going to take the bicarb. Bicarb is going to leave the cell. Ion leaving, we need to have a negative ion entering the cell in order to keep the net electrical charge of that cell the same. We didn't talk about this in class, but somebody asked at the review session yesterday, what would happen if the chloride shift didn't happen? So here is why. Think way back to chemistry. If we have a reaction that can go either way, if we take one of these, okay, so as bicarb is leaving the cell, that helps us to convert more CO2 into bicarbonate. If the chloride shift went away and bicarb convert CO2 into bicarb, we wouldn't be able to transport it in the blood, and now that CO2 would build up here in the tissue. So that will continue to convert CO2 into bicarb.
So you may wonder, hey, what's she talking about class and all that? It's because when you go to any medicine, you go to medical school, you go to nursing school, whatever school you go to, people seek out these guys who do essentially tutoring, right? What's that one Karina talked about? Clutch prep or whatever. Anyway, they tutor because the professor to clarify everything. That happens all the time. You're not going to get away from that. All right. So you're not going to learn everything and say, hey, this is the way it happens, and then so you have to go outside from an outside source to do it. So you're always MedCram is one of them, and then you have a bunch of these that put on by nursing students and nurses, and little symbol, those two arrows means that it's reversible, right? Chloride leaves the bloodstream and is excreted, and that's the reversal of the chloride shift. You just reverse that formula that she had there. Oh, next class I'm going to give you a test over the chloride shift, right? I mean, we're going to talk about it, but the significant part, if that didn't happen for some reason, then we'd have a buildup of CO2 in the tissue. And again, that's for another day. We're just in anatomy intro, right? Let me move back over here.
So that does happen, like in certain people, like it can happen?
That happens in everybody. It doesn't take place. That could be a possibility, but really the retention of CO2 is gets rid of CO2. There's multiple ways, but one way the body gets rid of CO2, the body's going to, these respiratory centers are going to recognize that and start breathing faster to get rid of the CO2. We'll talk about it at another date, but the other way is called the buffer system. Into the bloodstream to try to soak up some of that CO2. It's like a big, what's that you put in the water? Anti-acid. That's for another day. Once we get into respiratory emergencies, we'll talk about that. Right now we need to look at breathing. What's adequate? This is a big word. Adequate means that they're getting enough, they're receiving enough adequately to supply nutrition or oxygen to the cells. Adults, this is the only thing we're going to be concerned about for right now. Just remember children and infants. It's the normal respiratory rate of an adult. However, they only usually end of it. 22 would be hyperventilation. 24 would be the patient is 20 per minute. Right? So normal breathing, let's flip back. Would be good rise and fall of the chest, good expansion of the chest wall, no use of accessory muscles that we'll speak of here in just a second. So quiet, regular respirations. The way that you're doing right now is normal respirations. Okay? Breathe in. A patient shows up in the lips and initially it's a late sign. Right? Skin, when you look at the condition of normal skin, warm, pink, and dry. So normal skin is warm. Skin's clammy. We'll go into that. They're not. We probably have a definition. These are gasping respirations. This is not effective for sort of a snoring. It's very, very using accessory muscles. We don't breathe with our abdominal muscles in normal. Be the abdomen, you see them belly breathing, the belly sort of tugs and pulls like this, making the chest use of accessory muscles, sign diagonal respirations just occur. Sign diagonal respirations just occurred right. Picture nasal flaring, flares. Let me flare my nares, right? pediatric. Little guys' lungs are huge, and they get in the way. Right? Right? Carotid. This part in the neck right here. And mouth breathers. Okay? So you sort of sit there. Later, when we get into respiratory emergencies, you'll see kiddos in the hospital that this is. We just had it there, so I stuck an endotracheal. We just had it there, so I stuck an endotracheal. This is the epiglottis. I'm not really sure when we go look. Yeah, but this is one they didn't really clean the hook right there.